All right, so after J.J. Thomson did his experiments and he said, you know what, we've got positives and negatives in our atoms, Rutherford kind of built upon his experiments and looked a little bit more deeply at those positives and negatives, okay? So what Rutherford did was he said, okay, well, if we've got positives and negatives and we can strip them apart, I'm going to look at just spitting some alpha particles and see what happens to them. So an alpha particle is equal to a helium atom, right? So helium has 2 protons, and it's got it's got 2 neutrons as well, but it's got a 2+ charge, right? So what an alpha particle is really a helium atom that's had all of its electrons stripped away, okay? And so Rutherford took and he shot those helium particles into some gold foil, right? So gold foil, really thin gold, and he's able to see what happens to the alpha particles by having this screen around the outside. So according to Thomson's model, right, we would have positives and negatives all mixed about through our atoms. And if we shot this alpha particle, right, it's positively charged, it's probably maybe go straight through, maybe hit the whole thing and bounce off, right? But he didn't see that. Instead, Rutherford saw that almost everything went straight through to the other end, and a small amount maybe went over this way, and a small amount went over this way, and a really, really small amount got bounced back directly, right? And so Rutherford looked at this and he said, well, that doesn't really fit with Thomson's model, right? Thomson's model doesn't make sense. So Rutherford had to come up with a new model. And so because most of the particles were able to go straight through, Rutherford said, well, maybe the particles, the positive particles, are really all just in this tiny little spot in the middle, and all of the negative particles are going to be in the outside, right? So if it's a positive particle and it hits this really small little area, then it's going to get deflected. But most of the time, the particles are going to be able to go straight through to the other side. All right, so when he saw that the particles bounced back and got a little bit deflected, but mostly went through, he said, you know what, my positive, if I'm shooting positive particles there, my positive particles in the atom have to be in the center. So he said that positives are going to be in the nucleus. Okay? So his model then is that we've got a nucleus and a really open other part, and that's what makes up the atom. Okay? But he couldn't figure out any more information about the electrons other than that they were outside of the nucleus. Okay? What we needed to do was get an Einstein, actually. So Einstein, if we know, Einstein had won the Nobel Prize for the photoelectric effect. And what Einstein was able to show using math and experiments was that electrons, they could be shot off and they could interact with energy. They were the ones, if we added some sort of energy to it, right, light or heat, the electrons were sometimes affected, okay? And so Niels Bohr said, ooh, that's really interesting. And he said, all right, well, I'm going to look and I'm going to give one type of part or one element. I'm going to put it into a small little container and I'm going to force electricity to run through it. And when that electricity runs through it, I'm going to see what color do I get out. So when we run electricity, right, electrons, we're running electricity through, gives it lots of energy. We run it through and it's going to emit some sort of light. And turns out that depending on what element we had in there, the light changed colors. And so Niels Bohr looked at it and he said, okay, let me look at those colors really closely. And he found that the color matched the element and that it was predictable. Each element always stayed the same color. And it always emitted a certain color. And that color was could be related to energy. And so Niels Bohr, he said, you know what? Electrons aren't just outside the nucleus, right? They're not just out here. They are actually in some sort of orbit. So this is probably something similar to what you've seen before. Okay? So what Bohr said, right, once he saw these specific colors being released, it was really, really distinct colors. He said, you know what, if that much energy is being released, that must mean that my electron, when it goes maybe from the third level down to the second level, it's going to release energy as a photon, right? It's going to release energy as a photon, and that photon that we see is going to be specific to this amount of energy. So he says that electrons travel in orbitals. And those orbitals have specific energy associated with them. They're quantized energy levels. So orbitals are quantized. When an electron is up here and it's going to drop down to the second energy level, it's going to release a photon, and it has to release all of this energy. It can't just go halfway. No, that doesn't work. It's got to go from this outermost energy level down to the second, or it could go all the way down to the first, right? So this means that electrons are traveling in these orbitals, and the orbitals must be quantized.